See here, we are going to use two atomic operations. First one is weight and signal. Okay. See what is meant by weight. Okay. The weight operation decrements the value of its argument. So decrements means generally we are going to use S minus minus. Oh, we are going to represent this one as minus minus. Okay. If it is positive, only we are going to decrease. Okay. While S less than or equal to 0, then we are going to decrease. If S is negative or 0, okay, if S value is negative or 0, then no operation is performed. Okay, this is one of the operation, atomic operation for we are using in the semaphores. Okay, weight S, while S less than or equal to 0, then we are going to decrement the S value. Okay, this is one operation. And the next one is signal. Okay, so the signal operation is incremented. So previous one is decrementing. So here the value of S is we are going to increment. The signal operation increments the value of its argument S. Okay, we are going to increment this value. Okay, by using these two operations, we are going to solve the critical section problem. Okay, so what are the various properties of a semaphore? Okay, so it generally semaphores may work with many processes. Okay, if you are working with semaphores, then we are going to use many processes, and it is simple and always have non-negative integer value. Okay, we are going to represent, whenever we are working with the semaphores, always we are going to use non-negative integer value. Okay, next one is we can have many different critical sections with different semaphores. We are going to implement different critical sections with different semaphores, and the next property is each critical section have unique axis semaphore. That means if you take one critical section, for the critical section we are going to access one semaphore. Next one is it can permit multiple processes into the critical section at once if desirable. If it is possible, then we are going to permit multiple processes into the critical section. Okay, these are the various properties of a semaphore. Okay, so next one is what are the various types of semaphores? Okay, first one is counting semaphore, next one is binary semaphore. See what is meant by counting semaphore? These are the integer values. Generally semaphore means it is an integer value. These are the integer value semaphore and have unrestricted value domain. These semaphores are used to coordinating the resource axis, where the semaphore count is the number of available processes. Okay, that means here there is no counting of the semaphores, whereas in the binary semaphore we are going to represent either 0 or 1. In the binary semaphores are like counting semaphores, but their value is restricted to 0, 1. Here in the counting semaphore there is no restriction of the values. Okay, if the resources are added, semaphore count automatically incremented, and if the resources are removed, then count is decremented in the counting semaphore. That means if your one resource is added, automatically semaphore count is incrementing. Okay, one resource is removed, okay, automatically count is decrementing in the counting semaphore. Okay, whereas in binary semaphore it is not like that. Okay, it is just like as a counting semaphore, but their values are restricted to 0 and 1. The weight operation only works when the semaphore is 1. The signal operation works only when the semaphore is 0. Okay, these two are the various types of semaphores. So next one is what are the various advantages of semaphore? Okay, first one is it allows more than one thread to access the critical section. So next one is semaphores are machine independent. It is not just like as a dependent. It is a machine independent. So next one is semaphores are implemented in the machine independent code of the microkernel. We are going to implement this is a microkernel structure also. So next one is they do not allow multiple processes to enter into the critical section. Okay, by using the semaphore we don't want to allow the multiple processes to enter into the critical section, and so next one is, as there is busy waiting in the semaphore, for example, if there is a busy waiting state in the semaphore, there is never a wastage of the process time and resources. Here there is no wastage of process time and resources. Next one is they allow flexible management of resources. It means that we are going to utilize the resources very flexible. Okay, that means we are going to utilize the resources very perfectly. Okay, so these are the advantages of the semaphores. Okay. So next one is what are the various classical problems of synchronization. Okay. There are some, when we are going to talk about the problems of synchronization, there are some classical problems that are comes under this classical problems. Okay. We can say those are the classical problems of synchronization. We can say all these are the problems of synchronization. Okay. First one is bounded buffer, or we can say producer consumer problem. So next one is dining philosopher problem. So next one is the readers writers problem. Okay. Those three problems we can call it as a classical problems of synchronization. Okay. The problems are we can call it as a classical problems of synchronization. Okay. So first one is bounded buffer, or we can say producer consumer problem. See, what does this means? That this problem is generalized in terms of producer consumer problem. See here, bounded buffer, or we can say it is a producer consumer, where finite buffer full is used to exchange message between producer consumer process. Here there are two processes are there. First one is producer process, next one is consumer process. These two processes are exchange the message by using the finite buffer full. That means we have left hand side we have producer buffer, at the same time right hand side we have consumer buffer. In between these two we have finite buffer full pool. Why? Because in order to exchange the data between producer and consumer, because the buffer full has a maximum limit. Here the size of the buffer full is maximum. Okay, we are not mentioning any size. This problem is oftenly called as bounded buffer problem. Okay, that means here we are going to use finite buffer full. We are not mentioning the size. The size is maximum. Okay, so the solution to this problem is creating two counting semaphores. Okay, we are going to create two counting semaphores, that is full and empty. Okay, to keep track of the current number of full and empty buffers respectively. Okay, we are going to use two counting semaphores, that is full and the next one is empty. By using these two semaphores we are going to solve the bounded buffer problem or producer consumer problem. Okay, see what the actually problem statement is. Here we can say it is a pool. Here producer and consumer, there is a buffer of n slot. Okay, here we have buffer n slot, and each slot is capable of storing 1 unit of data. Okay, and there are two processes running, namely producer and consumer. Here producer and consumer, which are operating on the buffer. Okay, this is the problem statement. Okay, a producer tries to insert the data into empty slot of the buffer. Okay, initially a producer is trying to insert the data into the empty slot of the buffer. A consumer, next one right hand side, a consumer tries to remove the data from the filled slot in the buffer. We have one empty slot. For the empty slot, the producer is trying to insert the data. What the consumer is doing, the consumer is trying to remove the data from the slot. As you might have guessed by now, those two processes won't produce the expected output if they are being executed concurrently. Here what will happen is, if those two processes can't perform at a time, okay, at a time only producer is trying to insert the data. After that only the consumer is receive the data from the buffer. Okay, there need to be a way to make the producer and consumer work an independent manner. Okay, if those two persons, that is producer and consumer, works at a time, then there is a problem of synchronization. So in order to avoid those problems, here what will happen is, at a time only producer can do their work, and at a time after that only the consumer will do their work. Okay, so it is the producer consumer problem. Okay, see the solution is one solution of this problem is to use semaphores. Okay, by using the semaphore we are going to solve this one. Okay, here empty and full, there we are going to use two buffers. Okay, empty buffer and full buffer. Okay, empty buffer is the producer side and the full buffer is we can say consumer side. Okay, a binary semaphore which is used to acquire and release the lock. At the same time, we are going to use the binary semaphore. Here, empty is a one operation that we can say it is a counting semaphore whose initial value is the number of slots in the buffer, and next one is full. It is a counting semaphore whose initial value is 0. By using this two empty and full semaphores, we are going to solve the producer consumer problem. Okay, so next one is a dining philosopher problem. Okay, see, this is also one of the classical problems of synchronization. Okay, so in dining philosopher problem is another classical synchronization problem which is used to evaluate the situation where there is a need of allocating multiple resources to multiple processes. Here, what is a dining philosopher problem is there are 5 philosophers sitting around the table. There are 5 philosophers are there sitting around the table. If you see here, 5 philosopher 1, philosopher 2, 3, 4, 5. Okay, here what will happen is in which there are 5 chopsticks or forks. Okay, 5 chopsticks are there. If you see, we have 5 chopsticks. If you see this diagram, we have chopstick 1, 2, 3, 4, 5. Okay, we can say it as a fork. Okay, kept beside them and a bowl of rice in the center. Okay, see, 5 philosophers are there, 5 chopsticks are there, or we can say forks. There is a rice in the center. When a philosopher wants to eat, okay, for example, if a philosopher wants to eat, he used 2 chopsticks or 2 forks. Okay, one from their left and one from their right. Okay, here this philosopher wants to eat the rice. What he has to do? Okay, he has to use one chopstick from this side and one more chopstick from this side. Okay, philosopher 1 wants to eat, he will take the left side chopstick and the right side chopstick. Okay, when philosopher starts eating, he will take two chopsticks, one from their left and one from their right. When a philosopher wants to think, he keeps down both chopsticks and their original place. Here, the work of the philosopher is eating and thinking only. Okay, whenever the philosopher is eating, okay, he will use the 2 chopsticks. One is from left, one is from right. One more work of the philosopher is he wants to think. Okay, whenever he is thinking, he kept down those 2 chopsticks at their original place. Okay, the work of the philosopher is eating and thinking. Okay, either that philosopher should eat or in the position of thinking. Okay, whenever he is thinking, he should keep down those 2 chopsticks into the table. Okay, here problem statement is there are 5 philosophers sitting around a circular dining table, P1, P2, P3, P4, P5. The dining table have 5 chopsticks and a bowl of rice in the middle. Okay, see, you have rice and middle. Okay, here at any instant the philosopher is either eating or thinking. Okay, what is the work of the philosopher? Eating or thinking. When a philosopher wants to eat, he uses 2 chopsticks, one from left and one from right. When a philosopher wants to think, he keeps down both chopsticks at their original place. Okay, see here, it is not possible. Okay, why? Because we have only 5 chopsticks. Okay, the solution to the dining philosopher problem is, from the problem statement, it is clear that a philosopher can think for a indefinite amount of time. That means he is in the process of thinking. But when a philosopher starts eating, he has to stop at some point of time, the philosopher in the endless cycle. That means there is no endless for the thinking or eating. Okay, here when a philosopher wants to eat the rice, he will wait for the chopstick of his left hand, pick up that chopstick, then he waits for the right chopstick and to be available, and then pick 2. After eating, he will puts both the chopsticks down. Okay, whenever the philosopher wants to eat the right, he will wait for the chopstick until he gets the chopstick only. He is ready to eat. But if here the problem is, if all the philosophers are hungry simultaneously, okay, if all the 5 philosophers wants to eat at a time, why? Because hungry simultaneously, and each of them pick up one chopstick, then deadlock situation occur. Because here deadlock means it is nothing but 5 only. We have 5 chopsticks. 5 are hungry at a time. Okay, there is no chance for use the two chopsticks. Then we can say that those situation is a deadlock. Okay, because they will be waiting for another chopstick forever. The possible solutions for this are, the solution for this one are, is philosopher must be allowed to pick up the chopstick only if both are left and right chopsticks are available. That means if the philosopher must allowed to use these chopsticks only when those two chopsticks, that is left and right chopsticks, are available. Allow only 4 philosophers to sit at a table. Okay, if you are allowing the, instead of 5, if you allow the 4 philosophers, then there is no problem of that deadlock. Okay, that is, if all the 4 philosophers pick up 4 chopsticks, there will be 1 chopstick left on the table. So one philosopher can start it, and eventually 2 chopsticks will be available. In this way, we are going to avoid the deadlock. Over here, the solution is simply instead of 5 persons, we are going to use 4 persons. Okay, whenever they feel hungry, they can eat easily. Okay, so this is dining philosopher problem. Next one is the readers writers problem. Okay, in this problem there are some processes, we can say reader and writer. Okay, the only read the shared data. The work of the reader is read the shared data and never change it. Okay, it don't have option to change. There are another process called writer, who may change the data in addition to the reading or inserting the data. Okay, here 2 processes. First one is reader. Reader is only read the data, read the shared data. There is no chance of writing, modifying the data. Whereas writer, they write the data. It means they may change the data. Okay, there is a shared resource which should be accessed by the multiple process. There are 2 processes, that is we can say reader and writer. Any number of readers can read from the shared data simultaneously, but only one writer can write the shared data. Okay, any number of readers can read, but only one writer can only write the data. When a writer is writing a data to the resource, no other process can access the resource. Okay, for example, when a writer is writing the data, okay, that means the reader is not reading the data. That means if when a writer is writing the data at a time, if at the same time the writer is also writing the reader is reading the data, means there is a problem of synchronization. That means when a writer is writing data to the resource, no other process can access the resource. A writer cannot write to the resource if there are non-zero number of readers accessing the resource at a time. Okay, that means at a time the reader can do, after that the writer can do. At a time we can't perform the reader and writer operations. Okay, next one is monitor. Okay, next topic is monitor. Okay, we are going to discuss in this monitor concepts in next class. Next class we are going to talk about monitors. See what is a monitor, see how this monitor will work. Next one is synchronization example. Okay.